Hey everyone, today we are going to talk about numbers or complex numbers in polar form. If you remember, way back probably in Algebra 2, you learned about complex numbers and how to graph them and what the magnitude is. So we'll just review that real quick. When you have a complex number, so let's say you have the complex number z is equal to 3 plus 4i. So you're graphing in the real axis and on the imaginary axis. So if you think of a complex number in general form in terms of a plus bi, a and b themselves are real numbers, but bi is the complex component where a is the real component. So if I was going to graph 3 plus 4i, I would go 3 in the x direction or along the real axis, and then I would go up to 4, which would be up here, along the imaginary axis, and that would be the point 3 plus 4i. And so we often want to find the magnitude of that, right? We want to know the size of it because it's really hard to understand what the size is when you're looking at it just as a number, right? It's very easy if you're just looking at the number 10 versus the number 100. It's very easy to see which is the larger number. But when you're talking about 3 plus 4i versus 1 plus 7i, how do you know which one is bigger, which one is smaller? We use this whole idea of the absolute value of a complex number. That helps us find the magnitude or the size of it. Okay, so when we talk about absolute value, what we're doing is the absolute value of a plus bi. And you can think of it as really, if you were to draw in a right triangle here, right, if you were to draw in a right triangle, what we're actually doing is, that's not very straight, but you get the idea. We're finding the distance from the origin, right? Absolute value is distance. When you're talking about a real number, it's just the distance from 0 on the number line. But when you're talking about a complex number, it has these two different components. So we're talking about the distance from the origin in the complex plane. Right? So I know that this distance is 3, and I know that this distance is 4, because it's 4 units along the imaginary axis. And if you think of Pythagorean theorem, you're just doing 3 squared plus 4 squared, and that'll get you the hypotenuse of that right triangle. But if you think about it from a formula standpoint, it's just the square root of a squared plus b squared, which is essentially Pythagorean theorem, right? If you have c squared equals a squared plus b squared, to find c, which is your hypotenuse, that's all that you're doing. So that's what this formula is for absolute value of a complex number, or to find the magnitude. So you'll see it expressed as the absolute value, or sometimes it'll just say find the magnitude of the complex number, and that's what it means. So in this case, it would just be the square root of 3 squared plus 4 squared, which we all know would just be 5, right? 9 plus 16 be square root of 25, and that would give you 5. Okay, so that is how you would do it. If, for example, you had one that was 2 minus 3i, and you were trying to find the absolute value of that, when you do that, we've got 2 squared. And even though there's a minus there, that doesn't really apply because we're talking just about the distance from the origin, right? So it would be negative 3 in the I direction, but that distance is 3. So it would just be 2 squared plus 3 squared, which would give you square root 13. And that would just be your answer. Now that's in rectangular form. That's stuff that you've seen before, but let's talk about how we convert those into a polar form. Okay, so if we start with some equations here, if we have cosine of theta is equal to a over r, and sine of theta is equal to b over r. And you might say, well, I'm not exactly sure where those came from. Think about this. If I were to take that same number, same complex number, and I were to graph it in the polar in the polar plane, right? This distance would be A, this distance would be B, this angle would be theta, and that distance would be r. So this would be A plus BI. And so that's a theta in there. So if we think about the cosine of theta as A over r and the sine of theta as B over r, that's where those two equations come from. Okay, and so what we can do with that is we can multiply both sides by r, so we end up with A is equal to r cosine theta, and here we end up with B is equal to r sine of theta. So these should look familiar. Before we had complex numbers, when we just had rectangular, we had x is r cosine theta and y was r sine theta. Same idea, except instead of the point xy, we have the complex number a plus bi. So instead of this distance being x and this distance being y, it's a and b. Okay, so it's really the same idea, stuff that we've done before. We can also then say that the tangent of theta, right, tangent of theta is going to be opposite over adjacent, so that's going to be b over a. So those formulas are going to help us to convert rectangular form into polar form and vice versa. So this is for complex numbers. So if I have the complex number z is equal to a plus bi, and then I went and substituted in what I have, that would be r cosine theta plus r sine theta times I. And so if I factored an r out of both of those terms, that would give me r cosine theta, and I'll just clean this up a little bit. I'm going to put the I before it so that it doesn't look like it's attached to just the theta. It's I times the sine of theta. So that's the notation that we use, and this right here is your polar form. Okay, that is your polar form. The r value is called your modulus. And theta is called the argument. So if you see that terminology, that's what it is. And theta is going to be from 0 to 2 pi, but strictly less than 2 pi. It can equal 0, but it won't actually equal 2 pi. Okay, so whenever we write our complex numbers, and we write them in polar form, that theta will never be greater than 2 pi. Okay, it's always going to be less than 2 pi. Okay, so let's do a couple of examples. The first example is, let's write this complex number in, that should say polar form, not complex form. Sorry about that. That should say polar form. Right, this is already in complex form. I want to write it in polar form. So to do that, I need r and I need theta. Okay, one other thing we didn't talk about back here is that if I look at the Pythagorean theorem here, I also have this equation r squared equals a squared plus b squared, right? If you look at that picture, or r is equal to the square root of a squared plus b squared. I forgot to include that in there as one of the equations that we will use. Okay, so in this example, I want to convert this into polar form. I need to find r, and I need to find theta. So the first thing I'm going to do is find r. I find r, I'm doing a squared plus b squared. Remember, the negatives don't matter because we're talking about distance. So when you do that, we've got 2 squared plus 2 squared, which then gives me square root of 8, which when you simplify that, that comes out to be 2 root 2. We also have tangent of theta is equal to b over a. That's one of our other formulas that we have. I know what b is and I know what a is, so I've got tangent of theta is equal to negative 2 over negative 2, which would just be 1. Right, the tangent of theta is 1. The angle that has a tangent of 1 is pi over 4. However, think about where this complex number is. If you were to graph the complex number, you're at negative 2, negative 2i, so you're down here in the third quadrant. So to write this in the third quadrant, it would be 5 pi over 4. Okay, so that's where you have to be careful. Make sure that you represent the angle in the proper quadrant. So our complex number in polar form would then be z is equal to 2 root 2 times the cosine of 5 pi over 4 plus I times the sine of 5 pi over 4. Okay. The next example is putting the complex number into rectangular form. So to put that in rectangular form, all I need to do is actually figure out what cosine of pi over 3 is and what sine of pi over 3 is. So it's actually much easier to go from polar to rectangular because we're just evaluating it. The cosine of pi over 3 is 1/2. The sine of pi over 3 is root 3 over 2. If I just distribute that 2, then I just end up with 1 plus I root 3. And that's my number in rectangular form. So that one is much easier to do. When we talk about products and quotients in polar forms, if I've got my two complex numbers, so the first one is represented with subscripts 1. So I've got r1 times cosine theta 1 plus I sine theta sub 1. And my second complex number has all subscripts of 2. Then the product is just multiplying them together. So z1, z2. Now, when you multiply your complex numbers together, you multiply the r's together, but then you add the angles. So it would be cosine of theta 1 plus theta 2 plus I sine of theta 1 plus theta 2. And for the quotient, z1 over z2, you have r1 over r2, and then instead of adding the angles, you're going to subtract the angles. So you've got cosine of theta 1 minus theta 2 plus I sine of theta 1 minus theta 2. So that is the product and quotient formulas in polar form. I'm about to run out of time. I did on your note sheet put 2 example problems. The examples are in the book, so if you want to read through the example problems in the book, and you can follow along with how they do that. I will try to make a video also of the example problems. If I can get that up in time, I'll get that up for you. But if not, those example problems on the next page of your notes are right out of the book. Okay, I'll try to get that up for you. But in the next video for the next class or tomorrow's class, we'll talk about powers of complex numbers in the polar form. All right, everybody, thanks. I'll get you next time. Take care.